red bush. Now, do you know what? I think this plywood might actually be Japanese. Oh, it's you. How's it going? Great to see you again. My name is Carl. Welcome to my workshop and welcome to my YouTube channel. Now, as you'll have seen in the last video that I made at Moravia, there have been reasons why I've not been able to get into the workshop recently. And I was hoping that this video would be showing you a completed gas turbine combustion chamber, and we'd be able to talk about that. Unfortunately, I haven't got that far with it. But what I've decided to do is put all the clips together that I've been taking as I've been building the combustion chamber and put them into a video, like a digest, to show you where I've got to with it now, and talk about a few bits and pieces along the way that I'm planning to do in the future. So without further ado, we'll get on with the video. It will be up to its usually high standards of mediocrity, so don't worry about that. And we'll have another chat at the end. Okay, enjoy. Now, I think you'll agree that that is a really stupid place for me to put my brew. It'll go cold. So let's get that shifted for a start. So what have we got here then? We have got everything set up to start making some parts for the combustion chamber. So we've got the birthday cake here, as I like to call it, this stack of bits, which is my Arduino controlled stepper motor rotary table. It's just a Vertex 6-inch rotary table that I fitted a stepper motor to. And I made, about 18 months ago, I made a video about this system, and there's the control unit for it. So you might want to go and have a look at that if you're interested. That's a video that I made which shows you how it works and shows the electronics and various other bits and pieces. So I've got my 6-inch 3-jaw mounted onto the rotary table with a single bolt all the way through the center of the rotary table, and then bolted up to the chuck through, I'll show you it, just through there. You can just about see it, see the nut. And it's more than capable of holding that in position for what we're doing. I've got the chuck sitting on a couple of parallels on the rotary table because there is a protuberance on the other side of the chuck. On the back side of the chuck, where the camlock pins go, there's kind of a raised portion, so got it sat on those parallels there. So everything here is concentric to the table. Clocked the chuck into the table, and then the other thing I did was, you can't see it now because I've moved it, but everything was then concentric with the machine spindle, so I clocked everything in so that it was all centralized. So what I've done here now is I've moved the table so that the machine spindle is now 45 millimeters from the center of the plate, because I want to put in 4 M8 clearance holes on a 90 millimeter PCD, and that is going to be for, you can just see over there on the right hand side sitting on top of the vise is this V-band flange, which is going to be the output flange on the combustor, where it's going to go into the where the hot gases are going to go into the turbine. So as I said, I think I've probably already explained why I'm going to do that. I should have done by now anyway, if my editing is correct. Where I got the plate from, this is 304 stainless steel, 3 millimeters thick. It's laser cut, and I got that, I'll just show you now, from a company called Main Road Metalwork Engineering, and here's their details. As I say, laser cut, it's very good. It's 150 mil diameter, and it's spot on. Nice edge to it. Not that it is too important because I'm going to weld it, but it is a very nice finish on the edge. So there's the details. Main Road Metalwork Engineering. Centurion Way in Leyland. I wonder if that's got anything to do with Centurion tanks. I don't know. But there you go. Anyway, there's their email address and their web address. So very happy with the stuff that I've received from them. So without further ado, we'll get on, and in fact, before we do, I'll just show you the controller. So I've got this set onto the angle menu. So when I move this switch to the right, the table's going to rotate through 90 degrees, and it'll do that as many times as I keep pushing that button or moving that button across. I could have set it to step, which means that I basically tell it how many divisions I want, and it moves the correct amount, but I just set it to move 90 degrees each time. So again, it's the same rules with any rotary table operation or any kind of dividing head operation, move in the same direction every time. So I've rotated the table round the direction that it's going to move a few times anyway to get it set up with the clock. So I've taken all the lash out of it, out of the drive, the worm drive inside. So I'll be moving in the same direction every time, and drilling the pilot hole with this I was going to say a spot drill then, but it's not a spot drill, it's a center drill, and then about an 8.2 I think for clearance for M8. So I'll get the first one done, and then I'll show you the table moving around. I won't film too much of the drilling because, well, you know, it's drilling a hole. Okay, so that is the first hole drilled. So we'll move it around 90 to the next position. There we are. Next hole. Right, so I spared you the gory details, but there's the finished product. That's the this will be the output end, the output plate with the V-band flange, 4 bolt holes around about that central point holding it on. The next thing we've got to do is to put this plate in the lathe and put a 63mm hole through the center there to communicate with this V-band flange, and then we'll weld the funnel or the transition section and the expansion joint onto the back of that, and that'll give us our exit for the turbine gases through this V-band flange. Well, I don't know what this is going to be like. I've got a 2.5 inch hole saw in the tailstock. I've got the previously drilled stainless steel plate in the chuck. I've just put a 6.4mm drill through the middle of it, through the center hole. So let's try and see if we can get this 2.5 inch hole through through this plate so we can get the funnel welded into it. I'll bring you back. Well, I am getting through it, but it is genuinely terrifying. 40 RPM, loads of lube, stopping every so often to let the chips clear. It is only cutting on 1 tooth, but it's getting through it. Right, I'm not going to put you through that torture. Well, there we are. The end result was not too horrific, despite it singing like a canary. I mean, I suppose I could have had it up against a wooden board and then on the faceplate, but you know, 6 of one and half a dozen of the other, really. The other way I could have done it would have been to have pressure turned it with a pressure chuck arrangement. But again, a bit scary, and this is really hard, this stainless steel. Incredibly tough. And I think all things aside, or all things being equal, the hole saw did a pretty good job and was probably the safest option for me at the moment. But it's worked reasonably well. That's more or less what I wanted. So that can be welded into there now. I've actually done a bit of weld prep on the inside there, just turned a little bevel with the boring bar coming in at an angle like this, so I don't have to take it out with a chuck, because it'll never go back in concentric, obviously. So I just did it all in one setting. So I've got like a 45-degree chamfer on this side. There's kind of weld prep for where it's going to be welded on the other side. Probably tack it on this side. Might weld it on both sides, actually. We'll see how we get on. Potentially weld it on both sides, yeah. Anyway, so we'll move on to the next one now. Well, I keep doing it, don't I? But, you know, wood's a better insulator, so at least it'll stay warm. So we're messing about with hole saws again. And you might think I was being a little bit disparaging of the hole saw when I had it in the lathe. but I wasn't, because at the end of the day it's actually the ideal tool for doing this job, because this 304 stainless steel sheet that we're going through, it's you know, it's pretty tough stuff. It's 200 Brinell, 200 megapascal is the yield strength, 500 or thereabouts megapascal UTS, and 40% elongation, so it's hard and tough. You know, it's difficult stuff to play with, really. And the hole saw is a sheet metal tool at the end of the day. I suppose I could have put it up in the lathe and tried to pressure turn it, but imagine the tooth loading on that single point tool that we would have taken to do that with this material. Whereas with the hole saw, think about something like a slitting saw, the tooth loading is much lower, you know, due to the sawtooth blades. And this is a Cobalt Starrett 4-inch job. We're making the threaded ring here now, essentially, for the combustion chamber flame tube cap to rest up against in the outer casing. So we're going to be using lubricant on this quite clearly, and we'll be running at about 100 RPM. So I'll bring you back when we're actually doing it. And what I should have said, of course, is that I've got the stainless sheet, or plate rather, it's screwed to this wooden board, which is then clamped to the milling machine table. So this is as flat as it needs to be for the job that we're doing. And I've already piloted the center mark out there with a 6.4, because it's a 1/4 inch pilot drill in the hole saw. Huzzah, we're through. Well, I needed some M8 nuts to weld on to the plates that we've made to secure everything together, and I don't have enough stainless ones, but I do have a lathe and I have some stock, so we're making some threaded inserts to weld on. Tapping drill for M8 is 6.8. So I'll just put the taper tap all the way in, and then I'll put the plug tap in. And once we've done that, we can start to part them off. Going to be about 6.5 mil thick each one, I think. Just about the same as an M8 nut, really. I'll bring you back. So parting each one off now. So we'll continue in this vein, I'll bring you back. So there you would have the finished threaded inserts kind of positioned where they're going to be when they're welded onto the rings. And Colin, if you're watching this, we've just been talking about this and I've just shown you it as a preview. So here they are. So I'm going to have some lunch now, and then this afternoon we'll get some of these welded on with any luck. So we're at Moravia, that's the local aviation museum to me, and we have here in front of us a cutaway of a Rolls-Royce Olympus engine that was used in the Avro Vulcan bomber. And here we can see the combustion chamber. So we can see the snout where the air enters from the compressor here, and we have a swirler here which creates a vortex of air in this front end of the combustion chamber. What that does is it draws combustion products back in to where the fuel injector is here in this position to sustain the flame. And here we have the primary holes that allow the air to come in and mix that 20% of air that mixes with the combustion products and with the fuel. And down here we have the tertiary holes to dilute that combustion, so that when the air goes through there into the turbine, which you can just about see the blades, it's nice and cool and it doesn't have any hot streaks in it, ready to drive the turbine. We've also got some cooling holes here which help with the secondary air inlet. And there we are. Rolls-Royce Olympus engine combustor. Well, hopefully now you've seen some clips showing how I made some of these parts, and I'll go through them all now and I'll just show you how they go together in a mock-up way, if you like. So this is what I would like to think of as the foundation ring for the outer can. So you'll have seen me in the clips machine these inserts, or these threaded bushes rather, and I'll bring it a bit closer so you can see. So what I've done is, obviously I hole sawed through the center of the this round plate, which was laser cut, and I bought that plate laser cut already from Main Road Engineering. And then I've obviously then made these bushes and welded them to it. So I've got the PCD there with M8 threads on it. And the idea is that this then fits over the end of what's the outer can, and that'll be welded in place like that. So the flame tube then fits through that hole. Now this isn't going to be the actual outer can. I've got a piece of stainless steel for that. This is mild steel, but I've cut this to length just to show you the mock-up. I haven't cut the stainless steel yet, but I will be doing that in the future. So then what we've got next, that's quite heavy, is basically this is internal to this portion, so that'll go on like that, rings like a bell underneath. This is the funnel that takes the hot gases from the flame tube and takes them down to the diameter required to get into the turbine on the turbocharger. And I've purchased this V-band flange, which is a 2.5-inch V-band flange, which is the size for the turbocharger that I've got. And then this bolt pattern here, I've obviously welded the funnel to the exterior of the lower plate, and then I've got this 90-degree bolt pattern, so that will then go on like that, and that fits onto the top of the turbocharger. This stainless steel tube here is for the flame tube, so this will have the hole pattern drilled in it, a la the board behind me there. And I'm going to go through a quick example of the calculation that I did to determine the diameter of these two components, because one of the subscribers a few weeks ago left me a message on one of the gas turbine videos asking if I could clarify how I worked that out. And it's all down to experiential engineering basically, and rule of thumb, but it is a calculation that I can demonstrate to you, so I'll show you that in a minute. So we're going to have a sleeve on here which will be welded to either to the inside of this tube or to the inside of the funnel, so that this can slide over that sleeve and it'll sit like that with approximately a 5mm gap for expansion. So what I'll do is I'll bring this piece of brass here that's just out of shot, it's in shot, I'll bring it in, and we can stand everything on this so you'll see the stack up of these components. So basically the V-band flange would be attached to the, if this is, we imagine this is the turbo flange. The V-band flange is on the turbo. We then have this bolted to the V-band flange, the funnel. So this will be welded internally, or externally rather, to the outer casing. So we then have the flame tube, which is a sliding fit on a sleeve in the funnel there. I'm gonna have to try and do this without knocking it all over. So yeah, that looks pretty central. The other thing that we have is the top cap for the flame tube, which will sit like that and will be welded around the outside. Now this top cap is made of the same plate, laser cut, as these two components. But what I've done here is I've drilled, you can see I've just spotted the holes for the M8s to go in that hold it onto the foundation ring at the top of the outer can of the combustion chamber. And then I've got 3 holes in the top here that are just spotted through. So that will be the fuel injector. One of them is for the spark plug and the other one is for a pressure tapping. So that will be welded to the top of there. And then this whole assembly, the cap and the tube, will slide through this central hole. So what I'll do now is I'll put the outer can on. So this outer can, I'll just try and do this without knocking everything over, will be sitting like this, and it'll be welded to that bottom ring, or that bottom circular plate if you like. Try and get it so it's relatively central. Yeah, that's good enough, just to give you an idea. Then the ring is obviously then welded to the top, and then the cap on top of that, which will be welded to the flame tube. So I'll bring you in now, handheld, and you can see what this looks like. There will be a hole around about probably 25mm up from the base through there, with a pipe welded to it, which then goes onto the compressor section, or the outlet of the compressor section of the turbine. That's where the air enters the interior of the can and then will go through the holes into the flame tube. So if I just quickly take this off again and show you, the idea is, you can do that without knocking it over, this bottom portion here of the combustion chamber, or of the outer can, the air will enter here, and it's then got a plenum here to sort itself out and then start running up the edges of the periphery of the flame tube and then into the combustion reaction. So I'll just put this back on and I'll bring you back in closer and give you a view inside to see what it looks like. Okay, so there's a view of the base of the combustion chamber. So that stainless steel ring will be welded to a stainless steel version of this outer can around this periphery here. And then you've got this V-band flange adapter bolted to the bottom of this stainless steel plate with some gasket between the plate and the flange. And then moving up, we look inside. Sorry about the handheld. There's the foundation ring with the PCD of M8 threaded bushes. This is a little bit out of alignment because nothing's square at the moment. I've just kind of cobbled it together to show you. But you can see there that gap between the flame tube and this foundation ring. That will be the expansion distance basically. So then you've got the upper cap, which will be welded to that flame tube. So that will sit on like that and be bolted in place, and then through here we'll have the fuel injector, a spark plug and a pressure tapping. So that's the stack up of the components for the combustion chamber that I've manufactured so far. Right, so here's the numerology, if you like, that was requested by one of my subscribers for the combustion chamber sizing, and I'll put the person's name at the bottom of the screen. I can't remember his name just off the top of my head, but all these calculations are done based on rules of thumb that have been used by many others before me to manufacture these gas turbines from a turbocharger, and they work and they're proven, so we're going to use them. So the flame tube diameter is based on 3 times the inducer area. So the inducer of the compressor on our turbocharger is 50 millimeters in diameter, which gives us an area of 1963.5 millimeters squared. So if we multiply that area by 3, we get 5890.5 millimeters squared. And if we then translate that area into a diameter, we get a diameter of 86.6 millimeters. So I've rounded that up to 90 millimeters for the size of tubing that I was able to get. You could make that exactly 86.6 by rolling your own tube, but to be honest with you, it wouldn't make a great deal of difference. It's easier just to round it up to 90 millimeters and buy a piece of off-the-shelf tubing. Now for the outer can diameter, which the air from the compressor runs into, as I showed you just now when we're looking at the stack up of the components, that comes from the flame tube diameter plus 50 millimeters, because that's going to give us 25 millimeters clear either side of the flame tube, so that when the air from the compressor enters, it's not going too fast as it runs into the gap between the flame tube and the outer can, because if it was doing that, we would lose dynamic pressure, which we want to force the air into the holes of the flame tube against the pressure of the combustion. So we're looking at this diameter here plus 50 gives us 140 millimeters, and I went with 150 millimeters for a piece of tube that I could actually buy. Now the flame tube length is 3 times the flame tube diameter, so 90 times 3 gives us 270 millimeters. And in my example, it comes out, once you take into consideration the cone to actually guide the gases down into the smaller diameter for connecting to the turbocharger turbine, it's round about 300 millimeters. But again, you know, this is open to some interpretation. So I hope that's cleared up how I went about sizing the different components for the combustion chamber. Well, I hope you enjoyed that. Wasn't much to it, but it's all I've got, I'm afraid. And that's literally all I have time for. I'm going back to work this evening, traveling this evening, and then I'll be on the ship tomorrow. So how do I feel about that? Not great, if I'm honest with you, leaving my wife behind, and but she's in a good place now. She's through the worst of it. She's actually got over the surgery quite well, very well in fact, and she will have radiotherapy to come, but hopefully I will be home for some of that, so that's good. And she's in a good place now, and she's assured me that she's quite happy for me to go back to work. That doesn't mean that I feel happy about it, but there it is. That's the way life goes, I guess. Now, I really hope you've enjoyed it. As I say, there's still about 80% of people watching these videos who aren't subscribed to them. So if you're one of those people, then please have a think about subscribing to my channel. I'd really like it if you did that, and it's a small thing to do, but it helps me immeasurably, I can assure you of that. And if you are subscribed, please click on the notifications bell so you get to know when I upload this stuff, so you can see what I'm up to. And basically that's all I've got for you today, and keep well, look after yourselves, look after the women in your life, as I said in the last video, and I'll see you all soon.